This video is the third in a series of videos exploring thermal transport and focuses specifically on conduction. Thermal transport mechanisms include radiation, convection, and conduction. Conduction involves particle-to-particle contact. It involves hot particles conveying their thermal energy to cold particles through contact. Thus, conduction is the least important mechanism in astronomy, as typically particles are very far apart in most astronomical objects, for example, in stars. Conduction is the most significant mechanism of thermal transport on Earth. Let's explore conduction using the following. Consider slabs aluminum and asbestos, a silicate material that was commonly used as insulation until it was found to be carcinogenic. Both slabs are of similar thicknesses, are mounted at the same distances above Bunsen burners, and we have placed a matchstick on top of each slab. If lit Bunsen burners are placed underneath the slabs simultaneously, which match do you think will ignite first due to the conduction of heat energy? Which match will ignite first? Please record your vote on a piece of paper and explain your reasoning for choosing this answer. Your instructor will now stop the video. We will speed up the frame rate and see that the match on the slab of asbestos lights in about a minute of time, while the match on the aluminum will take much longer. That may seem a little counterintuitive. Since asbestos is an insulating material, shouldn't heat move less efficiently through it? Yes, but heat is also carried away from the flame location less efficiently in asbestos as well. We can check this interpretation by viewing the slabs with an infrared camera. Note that in infrared light, high temperature areas show up as bright. So on the asbestos slab, the region directly above the burner, where the match was located, is quite bright, indicating that it is quite hot, while the surrounding area of the slab is not nearly as hot, indicating that the heat energy is not being conducted away from the flame location. On the aluminum slab, the region near the flame is not nearly as hot as on the asbestos slab, because it effectively conducts the heat away and the entire slab is imparting heat to the surrounding air. Physics and engineering courses typically talk about heat flow, energy movement over time, in simple objects like metal rods. The conduction, heat energy delta Q traveling between the ends over time delta T, is proportional to the cross-sectional area A of the rod and the temperature difference between the ends delta T equals T2 minus T1, and inversely proportional to the length L of the rod. The constant of proportionality kappa is known as the thermal conductivity, which is a measure of how well a substance conducts heat, and its values can be looked up for many common substances. Large values for substances like metals imply that heat moves easily through the substance, while small values for substances like insulation imply that it doesn't. The complete equation that relates these variables is shown, where the heat flow delta Q over time delta T is equal to the thermal conductivity times the cross-sectional area A times the temperature difference delta T divided by the length L. We can solve for kappa to easily identify its units as watts per meter degree Kelvin, as one of the meters in area cancels with the meter in length. Here is a table of thermal conductivities for common substances, and we can see that air has a very small value of thermal conductivity, meaning that little heat energy can move through it. Insulating substances like asbestos have very small values, and insulators commonly trap air inside. Conversely, metals like aluminum have very high values, allowing a lot of thermal energy to move through them. Let's discuss an application from astronomy making use of conduction concepts. The underside of the space shuttle gets very hot upon re-entry into the atmosphere. The ultimate solution was gluing tiles with very low thermal conductivity to the underside of the shuttle. These tiles were composed of silica fibers and a lot of empty space, giving them very low thermal conductivity as well as low weight. Here we have an actual space shuttle tile, and we can place it over a Bunsen burner and simulate the heat it would have experienced during an actual space shuttle re-entry. If we look at the heated tile with an infrared camera, we can see the glowing underside, indicative of high temperature. But note the dark upper side, indicative of low temperature, and the low thermal conductivity of the tiles, preventing the space shuttle from overheating.